Hello everyone, today I'm going to be showing you how I made this clock for my girlfriend's birthday called the compressor clock. Let's get into it. This year, my girlfriend wanted a clock for her birthday. She sent me a picture to start designing from, so I started going with a rectangular body and a wider screen. I then took some creative liberties and settled on this design for the clock. After that, I drafted what the UI would look like to get an idea of what kind of resolution the screen would need. I then wrote up a list of features that I knew the clock had to have. Next, I created a block diagram to start understanding what components I would need to achieve all the features on my list. I started by selecting sensors and chips for every feature, and then picked a microcontroller that would be the best fit for the job. I then sourced a part number for every single chip, and ensured compatibility between all of them. After drawing, I hopped into Fusion 360 to start the CAD model for this project. I began with a simple rectangle to get a good idea of the dimensions I wanted, and then started adding holes to allow light and sound to pass through, along with an opening for the temperature sensor. I then added a hole for the screen after deciding on its size, and placed a big knob for my drawings onto the side. This will be how you control the clock. Here's roughly what it should look like when it's done. Here's the final schematic for the PCB. This section's all about power. The fuel gauge gives me information on the battery, like what charge it's at and how much current is flowing out of it. The USB-C port allows you to plug in a cable and power the battery charger, which then safely charges the battery to the right voltage. The battery voltage is converted to 3.3 volts by this buck boost converter to power the rest of the system. Here's the LED display matrix. I designed the PCB that just has the LEDs on another software and got it assembled overseas. The way this works is that ones and zeros get shifted into these registers at the bottom to control the columns of the display, and then the rows are just controlled by these MOSFETs. This process is called multiplexing, and it works by just lighting up one row at a time, since I do not have enough pins to control every single pixel on the matrix at the same time. Here's some of the sensors that communicate over the I2C bus, which is just an easy way for devices to speak to each other. Here's the PCB fully laid out and routed. Here you can see the matrix display that sits on top of the PCB. This matrix display contains about 588 LEDs, and I got this assembled overseas because I do not nearly have the patience to hand assemble that many LEDs on board. Down in the left corner is the microcontroller. This is what's controlling the entire clock and shifting data into these shift registers along the board. Right here is the light sensor for automatic dimming of the display, and under that is a temperature and humidity sensor. This right here is the buzzer for the alarm and timer functions of this clock, and this golden chip right here is the real-time clock module. This module is the heart of the entire project, as it keeps time accurately by oscillating a small quartz crystal to keep the time. This particular module is interesting because it acts like a mini oven, heating the crystal to make sure it stays at the exact same temperature all the time, so that time doesn't drift due to temperature changes. Over here is the battery charger and the fuel gauge, and on the back here is the battery itself. This is a 21700 lithium-ion battery, and it powers the clock for about 10 days, which is pretty good considering there's over 500 LEDs turning off at hundreds of times per second. This connector will go to a dial that allows the user to control the clock, and this connector is for the USB-C port. Over here is the connector for the power button, and this is the buck boost circuit that regulates voltage to the rest of the system. These MOSFETs right here control the rows, turning them on and off for the matrix display. Here's what the PCB routing looks like, just in case you're interested. By far the most frustrating step of any project is assembly. Now, I forgot to film a bunch of stuff, but essentially, as things usually go, there were issues. I spent 2 days on one board just trying to figure out why it wouldn't work, just to find out that one of the balls on the one BGA chip on the board had a bad connection. I also later realized that I flipped my MOSFETs in my schematic, meaning I had to physically flip every one of my MOSFETs over during assembly, bend the leads the other way, and then solder them upside down, which is not fun. All that aside, things basically worked on the first board, which is always a relief. And here's some pictures I took because, again, I didn't really film anything for this part. But look, they look really good. This part was pretty fun. I did a bunch of revisions on the enclosure, and originally this was going to be made out of aluminum. But there's been a slight complication with the cost of aluminum. I already have issues paying a lot for shipping, but my body will not allow me to pay an extra $100. So we had to settle on PLA for this project, which broke my heart, but it still turned out pretty sweet, so I'll live. Here's me assembling the clock. The rotary encoder, USB-C port, and power button all plug into the PCB. The power button and USB-C port are mounted to the backplate beforehand. To protect the matrix display, there's a laser cut piece of acrylic that goes inside the enclosure that gets held in place by the PCB itself. Here's me screwing on the backplate, and here's me turning it on, and it works. Very nice. I made 4 of these clocks. I sold 2 of them, one to my dad and one to my lab tech Reza, to save a little bit of money for the cost of this project. This cost adds up pretty fast. And of course, one is for my girlfriend's birthday and the other one's for me. Most people don't really care about this part, and I don't really want to talk about it that much, so here's some fun facts. There's 11,686 lines of code, custom written in this project, and it's written in Bear C, and the link to the GitHub is in the description. That's all I got for you. Now the moment you've all been waiting for, the demo. I'm just not going to say anything, you can kind of infer what's happening here.